Black holes, one of the most baffling and peculiar phenomena in the universe, remain a subject of extraordinary review and interest among space experts and physicists alike. These celestial objects, defined by their monstrous gravitational pull and the total absence of light emission, represent a limit beyond which the known laws of physical science no longer apply. First speculated by Albert Einstein in 1916 as a consequence of his theory of general relativity, black holes were only theoretical until technological advancements allowed for their indirect detection during the 20th century. The turning point came during the 1960s, when astronomers studying the Ceres group of stars accidentally discovered an unusual celestial object, a brilliant blue star emitting high-energy X-rays. This star, orbiting an invisible companion, defied regular explanations until it was revealed to be in a gravitational relationship with a massive black hole, Ceres X1. The discovery of Ceres X1 provided clear evidence for the existence of black holes and marked the beginning of a new era of investigation into these cosmic enigmas. Ceres X1, located about 6,000 light-years from Earth, has staggering properties. It is incredibly dense and exerts a gravitational force so intense that not even light can escape its grasp. This defining feature earned it the name black hole, encapsulating the essence of these mysterious objects. Subsequent research has uncovered a variety of black holes scattered throughout the universe, with estimates suggesting that the Milky Way alone may harbor more than 100 million black holes. Despite their elusive nature, which makes direct detection challenging, astronomers have identified several candidates within our galaxy, ranging from stellar mass black holes formed from the remnants of massive stars to supermassive black holes located at the centers of galaxies. The gravitational influence of black holes extends far beyond their immediate vicinity, shaping the evolution of cosmic structures and influencing the fate of surrounding matter. Objects that venture too close to a black hole face a fate determined by its relentless force. They are drawn inevitably toward the event horizon, the final boundary where they are subjected to extreme tidal forces and ultimately consumed by the singularity at the black hole's core. This catastrophic interaction, known as spaghettification, is the extreme manifestation of a black hole's gravitational strength. As an object approaches the event horizon, the gravitational gradient across its length becomes so extreme that it is stretched and contorted into a filamentary shape resembling strands of spaghetti. The forces exerted by the black hole overpower the internal bonds keeping the object intact, causing it to disintegrate into a stream of matter that eventually merges with the singularity. Despite the allure of black holes as laboratories for testing the limits of physical theory, they remain shrouded in intrigue. The quest to unravel their secrets continues, driven by a desire to understand the fundamental nature of spacetime and gravity itself. In the vastness of the universe, black holes stand as silent sentinels, beckoning humanity to explore the depths of the unknown and expand the boundaries of human knowledge. Despite the tremendous distance separating us from the nearest black hole, roughly 1,500 light-years away, questions and concerns about their potential impact persist. In 2021, researchers achieved a monumental breakthrough by capturing the first clear image of a black hole, specifically M87, located at the center of the M87 galaxy. This remarkable achievement provided crucial insights into the nature of black holes and their elusive structure. The visual data revealed that black holes have complex layers, challenging the traditional perception of them as solitary entities of pure nothingness. Through meticulous analysis and imaging stitching, scientists identified 3 distinct layers within a black hole. At the outermost layer lies the event horizon, a critical boundary marking the point of no return. Once an object crosses this threshold, gravitational forces become insurmountable, ensuring its inevitable fall into the black hole's depths. Moving inward, the photon sphere constitutes the second layer, where light orbits the black hole in perpetual captivity. Any photons that venture into this realm succumb to the overwhelming gravitational pull, trapped forever within the black hole's cosmic embrace. At the heart of the black hole lies the singularity, the third and final layer, where the laws of physics break down. The familiar laws governing the universe cease to apply, plunging researchers into a realm of profound uncertainty and theoretical speculation. The complexity of black holes and their inherent variability presents significant challenges to our understanding. While they share a common 3-layer structure, each black hole exhibits unique characteristics and behaviors, defying simple categorization. As such, traditional methods of scientific inquiry prove insufficient for studying these cosmic behemoths, necessitating innovative approaches to unravel their mysteries. Indirect observation remains the primary means of studying black holes, as direct investigation is rendered unfeasible by the immense barriers posed by their gravitational forces. Attempts to launch probes into black holes would inevitably result in their destruction, crushed into obscurity by the relentless forces at play. Nevertheless, researchers persist in their quest to decipher the secrets of these cosmic giants. Various theories, ranging from stellar collapse to cosmic dynamics, offer tantalizing glimpses into their origins and behavior. Notably, NASA's study of the cosmic center of M87 revealed compelling evidence of a supermassive black hole exerting its gravitational influence over vast cosmic scales. Despite these challenges, the pursuit of knowledge continues unabated, driven by humanity's inherent curiosity and thirst for understanding. While the enigma of black holes may elude simple comprehension, the steadfast dedication to scientific inquiry promises to illuminate the darkest corners of the universe, unraveling the profound secrets hidden within. Roy Kerr's groundbreaking work in 1963 presented a paradigm-shifting perspective on black holes, proposing a revolutionary theory of rotating black holes that defied conventional understandings. Central to Kerr's model was the concept of the ergosphere, a region surrounding the black hole where divergent forces balance gravitational collapse, preventing matter from collapsing further inward. This novel domain displayed curious deviations from traditional physics, hinting at the profound mysteries concealed within black holes. However, the most intriguing implication of Kerr's theory was the prediction of an Einstein-Rosen bridge, informally known as a wormhole. This hypothetical structure represents a potential gateway through spacetime, offering a conduit between distant regions of the universe, or even parallel universes. The idea of wormholes stems from the intricate interplay between reality as described by Einstein's theory of general relativity. At the forefront of this endeavor lies string theory, a bold and mathematically rich framework that attempts to unify all known physical phenomena by positing that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings resonate at different frequencies, giving rise to the particles and forces observed in nature. String theory naturally incorporates gravity, making it one of the most promising candidates for a theory of everything, a theory that could bridge the gap between general relativity, which governs the large-scale structure of the cosmos, and quantum mechanics, which rules the subatomic world. Yet despite its elegance, string theory remains largely theoretical and untested, constrained by the limitations of current experimental technology. Its implications, however, are staggering. It suggests the existence of extra dimensions, beyond the familiar three dimensions of space and one of time, which may be compactified or curled up at scales too small to detect. These dimensions could harbor entire universes with different physical laws, a proposition that dovetails with the multiverse hypothesis. Black holes offer a natural laboratory for testing these high-level theories. At their core, where gravitational forces crush matter to a singularity, the effects of quantum mechanics and general relativity become inseparably intertwined. One of the most compelling puzzles in modern physics, the black hole information paradox, famously articulated by Stephen Hawking, challenges our understanding of both disciplines. According to classical theory, information that falls into a black hole is lost forever, violating the fundamental quantum principle that information must be preserved. To address this paradox, theoretical physicists have proposed various solutions, including the holographic principle. This concept posits that all the information contained within a volume of space can be represented on its boundary, much like a hologram. Applied to black holes, it suggests that the information consumed by a black hole is not destroyed, but rather encoded on its event horizon. If validated, this idea would have profound implications not only for black holes but for our understanding of the universe as a whole. In 2022, further support for the holographic principle came from advances in quantum gravity research, particularly through the study of ADS-CFT correspondence, antidesita conformal field theory, a duality proposed by physicist Juan Maldacena. This duality provides a powerful mathematical tool for exploring the nature of space, time, and information in extreme conditions. It suggests that a gravitational theory in a curved spacetime, like that surrounding a black hole, can be equivalent to a quantum field theory in a lower-dimensional, flat spacetime, offering a window into the heart of quantum gravity. Ultimately, black holes remain cosmic crucibles, gateways not only to understanding the most extreme conditions in the universe but also to potentially unlocking the deepest truths of reality itself. Their study challenges our assumptions, pushes the boundaries of mathematics and physics, and invites us to confront the limits of knowledge. In their silent, lightless hearts may lie the answers to some of the most profound questions ever asked by humanity. The future of black hole research is filled with promise. With the development of next-generation telescopes, such as the James Webb Space Telescope and upcoming gravitational wave detectors, scientists hope to detect and analyze black hole mergers, peer deeper into galactic cores, and perhaps one day, however distantly, test the very fabric of spacetime itself. As we stand on the precipice of discovery, black holes continue to beckon with the promise of revelation, offering a mirror in which the universe reflects its most hidden truths. Stands the renowned theoretical physicist Myoku, whose groundbreaking work has propelled the study of superstring theory. Superstring theory represents a dramatic departure from conventional ideal models, hypothesizing that fundamental particles are not point-like entities but instead microscopic vibrating strings. These strings, much like the strings of a musical instrument, resonate at specific frequencies, giving rise to the various particles and forces observed in nature. In this paradigm, the universe becomes akin to a grand symphony, with each particle corresponding to a unique harmonic resonance of these fundamental strings. One of the most striking implications of superstring theory lies in its potential to explain the enigmatic phenomena associated with black holes, wormholes, and other exotic solutions to Einstein's equations of gravity. As strings traverse the fabric of spacetime, their dynamic motion leads to the formation of gravitational singularities and topological anomalies. However, the elegance of superstring theory masks its inherent complexity, as it necessitates the existence of additional dimensions beyond the familiar three spatial dimensions and one temporal dimension. These extra dimensions, hidden from direct observation, present a significant challenge to human intuition. Nevertheless, applied models such as the analogy of fish inhabiting a two-dimensional lake provide a glimpse into the elusive nature of these higher-dimensional realms. The compactification of these extra dimensions, akin to the folding of a rolled-up piece of paper, renders them imperceptible at everyday scales, yet their influence permeates the very fabric of reality. While the precise nature of these hidden dimensions remains elusive, their theoretical presence offers a promising explanation for the complex structures and anomalies observed in the universe. Furthermore, the mathematical underpinnings of superstring theory have sparked a renaissance in mathematical physics, revealing profound connections between dynamic mathematical patterns and physical phenomena. Indeed, the pursuit of a theory of everything has catalyzed the union of disciplines, shedding light on the deep interplay between mathematics and the natural sciences. Despite its theoretical elegance and scientific potential, superstring theory remains an untested framework awaiting experimental validation. The elusive nature of extra dimensions presents a formidable barrier to experimental verification, relegating superstring theory to the realm of mathematical speculation. Nevertheless, the audacious vision of superstring theory continues to captivate the minds of researchers and enthusiasts alike, enticing humanity to embark on a journey of intellectual discovery and exploration. As we venture deeper into the known domains of theoretical physics, guided by the illuminating beacon of superstring theory, we confront the vast mysteries of the universe, poised on the threshold of a new era of understanding and enlightenment. The task of unraveling the secrets of quantum black holes has long perplexed physicists, representing a monumental challenge to our understanding of the fundamental nature of the universe. Despite numerous efforts to tackle this riddle, the live solution has remained beyond our grasp, prompting Edward Witten of the Institute for Advanced Study at Princeton to describe superstring theory as the 21st century physics that accidentally fell into the 20th century. However, recent advancements have injected new hope into the quest for understanding quantum black holes. Several groups of physicists have independently reported a significant breakthrough, revealing that string theory could offer a comprehensive solution to the problem, albeit within the more constrained context of 2 dimensions rather than the full 10-dimensional framework set forth by conventional superstring theory. While this represents a promising step forward, the quest for a complete resolution remains ongoing, with the complexities of the situation presenting substantial obstacles. The search for a unified theory of everything beckons us to probe the deepest recesses of cosmic existence, where the boundaries between reality and theory blur and the secrets of the universe await discovery. The study of black holes carries profound implications for our understanding of the universe, challenging our notions of reality and raising questions about the nature of existence itself. The interplay between black holes and other astronomical phenomena, such as neutron stars and gamma bursts, reveals the intricate processes at work in the cosmos. As researchers delve deeper into the quantum properties of black holes, they encounter profound paradoxes that test the limits of modern physics. Chief among these is the black hole information paradox, which questions whether information that falls into a black hole is truly lost forever, an idea that directly conflicts with the principles of quantum mechanics. This paradox has become a central battleground where the theories of quantum mechanics and general relativity collide. Superstring theory, along with its extended framework M-theory, offers potential pathways toward resolving this tension. Within certain formulations, it is suggested that information is not lost but rather encoded in the quantum fluctuations of the event horizon or perhaps radiated back through what is now termed Hawking radiation, albeit in a highly scrambled form. Such insights hint at a deep and subtle mechanism by which nature preserves information, even in the most extreme conditions imaginable. The implications of resolving the information paradox extend beyond black holes. They speak to the very fabric of spacetime, suggesting it may not be a smooth, continuous manifold as once believed, but rather an emergent property woven together by more fundamental quantum processes, possibly involving entanglement, holography, and non-locality. Indeed, the holographic principle, which posits that all the information within a volume of space can be described by the information encoded on its boundary, has gained considerable traction. Developed in part from insights in string theory and black hole thermodynamics, this concept suggests that our seemingly three-dimensional universe may, at its deepest level, be a projection from a more fundamental two-dimensional reality. This bold reconceptualization of reality challenges not only our scientific assumptions but also our philosophical understanding of existence. Are we living in a vast, cosmic illusion? If space and time are emergent rather than fundamental, what then constitutes the ultimate substrate of reality? In laboratories and institutes across the globe, physicists are developing experiments, however indirect, to test the edges of these theories. While the direct detection of extra dimensions or strings remains elusive, advances in high-energy physics, cosmology, and quantum computing offer new tools for exploration. Gravitational wave observatories, particle accelerators, and quantum simulators are now at the forefront of this search, probing conditions that mimic the earliest moments of the universe, where these grand theories may reveal their truths. Yet, despite the daunting challenges, there is an undeniable optimism. For in seeking to unify the forces of nature, from the majestic gravity of black holes to the ethereal dance of quarks and leptons, we are not merely solving equations, we are unfolding the narrative of the cosmos. We are discovering our place within it. Superstring theory may be speculative, incomplete, and controversial, but it is also visionary. It represents humanity's boldest attempt to peer beyond the veil of the observable, to articulate a cosmos where every particle, every force, every law is but a note in a sublime symphony of vibrating strings. And as we continue to explore this grand theory, one truth becomes increasingly clear. The universe is not just stranger than we imagine, it is stranger than we can imagine.